Okay, so now we are up to the fifth video in this series, and this one is going to be about continuity. And I'm just going to briefly write down the definition for continuity, but again, I assume that everyone watching this already knows the overall ideas, and I'm mostly concerned with just going through a bunch of exercises. But a function is continuous at a number a. This is on page 97 in the book. If the limit as x goes to a, f of x equals f of a, meaning you don't want a function to do something like this. This function is not continuous right over here, because that the limit as you approach a, let's say the limit is going to be some number, let's say 2, but f of a itself is going to be, I don't know, 5. So this function is not continuous. And well, now that we know the definition, the first question, which asks, write an equation that expresses the fact that a function f is continuous at a number 4. Well, it's very simple. The limit as x goes to 4 of f of x equals f of 4. That's it. Second problem, if s is continuous on the interval negative infinity to infinity, what can you say about its graph? Well, I guess what you can say, okay, so you have your function, and it's continuous from infinity to negative infinity over here. So when you draw your function, however you draw it, you just draw it like, you can basically draw it without lifting your pen, I guess, or without jumping in the drawing. You never, again, have to lift your pen and jump to another point. You can just draw the entire function, and if you had an infinite piece of paper going this way, an infinite piece of paper going that way, you can draw the entire function without, I guess, lifting your pen. So now I'm going to go to problem 5, which says, sketch the graph of a function that is continuous everywhere except at x equals 3 and is continuous from the left at 3. So being continuous from the left means that the limit as x goes to 3 from the left of f of x is equal to f of 3. So the way we would sketch this is, let's say this is 3, our function would go do something like this, and at 3 it's going to be equal to the limit from the left. This is the limit from the left of 3, and then it's going to jump, let's say, to here and continue. That's how we would sketch that graph. Problem 6 says, sketch the graph of a function that has a jump discontinuity at x equals 2. So, okay, at x equals 2 has a jump discontinuity and a removable discontinuity at x equals 4. So this is x equals 4, removable continuity, let's say something like that, but it's continuous everywhere elsewhere. So you have your function that goes something like this, and it's a jump discontinuity over here, which means that you can't like fix it by just moving a single point. So it would go something like this, and then it's going to do something like this. You know what it's going to do? This is 4. It's going to do something like this, and now it's going to have a removable discontinuity of 4, and then it's going to continue. Not very hard. Okay, so the problem I'm going to do is problem 7. A parking lot charges $3 for the first hour or part of an hour, and $2 for each succeeding hour or part, up to a daily maximum of $10. Sketch a graph of the cost of parking at this lot as a function of time parked there. So we have our graph, and we have 1 and hours, 1, 2 hours, 3, 4, 5, whatever. And then over here we have the cost. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. So first is you don't charge at all at 0. And then for the first hour, part of the hour you charge up until the hour, the full hour. And then you jump to, so if you just finished an hour, you don't charge anything. But if you start your hour, then you pay that amount until the next hour. Then you jump up again. The same thing happens. This is okay, and then jump up again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you jump up again to okay. Okay, I don't know, something's not working, but the overall point I think is well understood. And then at some point the 10, whatever, it just is flat, whatever. Okay, so problem 8, let's just go through it quickly. So the question is, explain why each function is continuous or discontinuous. The temperature at a specific location as a function of time should be continuous because temperature is continuous, and as you move along in time, as I move along in terms of time, as time moves, the temperature goes up and down, but it goes up and down smoothly. The temperature, so that's A. For B, the temperature at a specific time as a function of distance due west. So again, as you travel in the distance, the temperature does not change that dramatically. So again, it should be continuous. The altitude above sea level as a function of the distance due west from New York City. Well, I don't believe the sea moves like that drastically, and I don't think as movement, when you move due west, the sea level will change that quickly. I mean, it's the sea level, so it should also be continuous. The cost of a taxi ride is a function of the distance traveled. Well, this is not continuous because the cost jumps. You start at a certain cost, and every amount of time, based on distance, it just jumps up. It doesn't change in a continuous way. It goes from $5 to suddenly $7 to $9, whatever. The current in the circuit of the lights in the room as a function of time, that is also not continuous because you can turn off the light and suddenly you go from having a current to not having a current at all. Okay, so that was problem 8. Sorry if it was a little boring. Problem 9, we say that, so suppose that f and g are continuous functions, and we have that f of 3 equals 5, and the limit as x goes to 3 of 2 f of x minus g of x is equal to 4, and we want to know what g of 3 is. So we know that the lim as x goes to 3 of f of x is equal to f of 3 is equal to 5, and we also know that the lim as x goes to 3 of g of x is equal to g of 3. And this, by the limit rules, can be written in terms of 2 lim x goes to 3 f of x minus lim x goes to 3 g of x. And that can be written in terms of 2, and this we know is 5, so this is 10 minus and this we know is g of 3. G of 3 and we know that all this is equal to 4. So we know that negative g of 3 is equal to negative 6, or g of 3 is equal to 6. Okay, next problem. So problem 10. Use the definition of continuity and the property of limits to show that the function is continuous at a given number a. So we want to show that f of x equals x squared plus the square root of 7 minus x is continuous for a equals 4. So what we want to show is that the limit as x goes to 4 of x squared plus square root of 7 minus x is equal to 4 squared plus 7, the square root of 3, is it? Sure. We want to show this, right? And this follows straightforward by the limit laws and all that, so there's nothing really to show there. And yeah. So let's do a slightly more difficult problem, problem 13, which states, use the definition of continuity and the properties of limits to show that the function is continuous in the given interval, and the function is, for 13, f of x equals 2x plus 3 and x minus 2, and we want to show it's continuous on the interval 2 to infinity. So let's imagine, so we know that the limit as x goes to some number a of f of x over g of x is equal to the limit as x goes to a of f of x over the limit as x goes to a of g of x, provided that the limit as x goes to a of g of x does not equal 0. Right? That's one of the limit laws. So we can say that the limit as x goes to 2. So, sorry, we can say that the limit as x goes to any number, let's say c, where c is an element of 2 comma infinity, of f of x for us, which is 2x plus 3 over x minus 2, is equal to the limit as x goes to that number for 2x plus 3 over the limit as x goes to that number for x minus 2, simply because that c is in the interval 2 infinity, from 2 to infinity, but not including 2. And this is 0 only when x equals 2. So this is fine. So this statement is fine. And now we are dealing with two polytopes. So this, by the limit laws, is going to be equal to 2c plus 3 over c minus 2, which is exactly what we want. We want this to say that this is continuous for any c where c is in here. To say that it's continuous is to say that the limit as x goes to c of 2x plus 3 over x minus 2 is equal to 2c plus 3 over c minus 2, which is exactly what we got. So proved that it is continuous in that interval, simply because that we can use the limit law for quotients, because that we're not dividing by 0, and the limit in the bottom is not going to 0. So the next problem I'm going to do is problem 15. Explain why the function is discontinuous at the given number a. Sketch the graph of the function. So we have f of x is equal to negative 1 over x minus 1 squared, and we have a equals 1. So for x equals 1, we want to show that this is discontinuous. So basically over here, if you take the limit as x goes to 1 of negative 1 over x minus 1 squared, what you're going to get is negative infinity. Because that over here, where you're dealing with approaching, if you approach from both the left and the right, you're dealing with a really small positive number because it's being squared. And over here you have a negative, so you are dividing by a really small positive number and taking the negative of that, which gets you to negative infinity. But 1 over 1 minus 1 squared, or in other words, negative 1 over 0 is undefined. So that's why we have a discontinuity there. Let's look at problem 16. This is on page 106 in the book, in the description. F of x is equal to 1 over x minus 1 if x does not equal 1. And it's going to be equal to 2 if x equals 2. Oh, going back to the previous problem, if we sketch it, it's going to look something like this. 2 at 1, it's going to negative infinity, so it's doing something like that, and going to negative infinity. Okay, so this function, so let's show that it is discontinuous at, and we want to show it's discontinuous at a equals, sorry, this is 1, a equals 1. So the limit as x goes to 1 of f of x is going to be plus and minus infinity, or, well, not really. Okay, so again, we're dividing by 0, but we're dividing by a 0 which is by something very small, which is positive. That's when we come from the right. And we're dividing by something really small that is negative. That's when we're coming from the left. So this limit doesn't really exist, and it's really the limit as x goes to 1 from the left of f of x is equal to the limit as x goes to 1 from the left of 1 over x minus 1, which is equal to negative infinity, and the limit as x goes to 1 from the right of f of x is equal to the limit as x goes to 1 from the right of 1 over x minus 1 is equal to positive infinity. But f of 1 is equal to 2, because that when x is 1, we just choose 2. In the two previous cases, x was not equal to 1, so we're using this part of the function. So we don't have that the limit as x goes to 1 of f of x is equal to 2, right? This is not true, so we have a discontinuity. That is problem 16. Let's look at problem 17. So now we want to show that for f of x equals 1 minus x squared, or 1 over x. So this is if x, previous problem, if we graph the function, it would look something like, okay, let's erase this for a second. Ooh. For the previous problem, if we graph the function, so at 1 we're going to positive infinity and to negative infinity, but at 1 itself we're exactly at 2. So this is how your function would look. Okay. So now we are looking at problem 17, which says something like this. So we have f of x is equal to 1 minus x squared if x is less than 1, and 1 over x if x is greater or equal to 1, and we want to show at a equals 1 that there is a discontinuity. So let's take, first thing, let's take the limit. Well, we can, so let's first take the limit as x goes to 1 from the left of f of x, and this is equal to the limit as x goes to 1 from the left. Now if x is on the left, then it is less than 1. So for f of x, we choose this, so it's 1 minus x squared, and this is equal to 0. So that's the limit. Now if we take the limit as x goes to 1 from the right of f of x, we get the limit as x goes to 1 from the right of 1 over x, and we get 1. And f of 1 itself, because we have equals over here, is going to equal to 1. So first thing, the limit doesn't exist. So the limit as x goes to 1 of f of x does not exist, which already tells us that there is discontinuity. But definitely you do not have the limit as x goes to 1 of f of x equal to 1. You don't have this, or to f of 1. You don't have this. You have discontinuity. Let's look at problem let's look, and for the previous problem, the graph would look something like this, but then exactly at 1, you're not going to have that. At 1, you're going to have a jump, and it's going to be 1, and then it's going to do whatever. Okay, next problem. So we have f of x equals x squared minus x over x squared minus 1, and this is if x does not equal 1, and this is if x equals 1. And a is equal to 1, so we want to show that there's a discontinuity at 1. So the limit the limit as x approaches 1 of f of x is equal to the limit as x approaches 1 of x squared minus x over x squared minus 1, which is equal to x times x minus 1 over x squared minus 1, limit as x goes to 1. This is equal to the limit as x goes to 1 of x times x minus 1 over x plus 1 times x minus 1. And so these cancel, and this is equal to the limit as x goes to 1 of x over x plus 1. And this is equal to a half. So the limit is equal to a half, but if we take f of 1, we get 1. So we have the limit as x goes to 1 of f of x does not equal f of 1, or in other words, doesn't equal 1 because the limit is equal to a half. This is equal to 1, and this is equal to a half. And that's why we have a discontinuity. But interestingly enough, if we change this to a half, then this function is continuous at 1, surprisingly, because the limit agrees with the number over here with f of 1. Next problem. That was problem 18. Now I'm going to do problem 19. F of x equals cosine x if x is less than 0. 0 if x is equal to 0, and 1 minus x squared if x is greater than 0. And we want to know if there's a discontinuity at a equal 0. So if we take the limit as x goes to 0 of f of x, we have to do this in 2 steps. We have to do it going from the left, which will be this, when x is smaller than 0, and coming from the right, which is this, when x is bigger than 0. So in order to do this, so first we want to even know if we have a limit. So the limit as x approaches 0 from the right, let's do the left first actually, from the left of f of x is equal to the limit as x approaches 0 from the left of cosine x, because that when x is approaching 0 from the left, it's smaller than 0, and this is what we get when x is smaller than 0, and this is equal to cosine of 0, which is equal to 1. Now the limit as the limit as x approaches 0 from the right of f of x is equal to the limit as x approaches 0 from the right of 1 minus x squared is equal to, because we're dealing with a polytope, 1 minus 0 squared, which is equal to 1. So the limit exists. So the limit as x approaches 0 of f of x is equal to 1. The limit exists, but f of 0 is 0 because of this. So we have a discontinuity, because that the limit as x approaches 0 of f of x is equal to 1 is not equal to f of 0, which is equal to 0. But if we change this to 1, now we no longer have a discontinuity. Now this function is continuous. Next problem, problem 20. So we have f of x equals 2x squared minus 5x minus 3 over x minus 3, and this is if x does not equal 3, and it's going to be 6 if x equals 3. So, and we want to find what we want to prove that it's discontinuous at 3. We know they tell us it's discontinuous. We want to prove it's discontinuous. So we want to find the limit as x approaches 3 of f of x, which as we're approaching 3, we're not equal to 3, is this right there. So it's going to be 2x squared minus 5x minus 3 over x minus 3. We want to find the limit for this, and well, on the top we have 15 over here, and this is 9, this is 18 minus 18, so it's 0. It's basically we're approaching 0, 0, so a limit might exist, meaning we cannot say that this is undefined. A limit might actually exist. So now let's check to see what that limit is. So again, I'm assuming that there is a number, so there's a thing x minus 3, that if I multiply by something, I'm going to get 2x squared minus 5x minus 3, because I assume that they want me to cancel this part with something over here. That was a good assumption. I mean, in practice, like, might be a little people might be a little disturbed that that like we are using this trick, but it's a fine assumption because they want you to figure it out. Other you can use calculators and computers for all of this. So if you're going to do it analytically and like by hand, they're going to make it easy for you. So this should be 2x to get this 2x, right? So we have down here 2x squared. And now when I take negative 3 times 2x, I get negative 6x. So I want to get rid of the negative 6x. So I want to put over here, I want to put, well, oh, sorry, I don't want to get rid of the, I don't want to get rid of the entire 6x. I just want to get rid of 1. So I want, let's assume that I have a plus 1 over here. So now I'm going to have x times 1, which will give me plus x, and then a negative 3 times 1, which will give me minus 3. Or in other words, I'm going to get 2x squared minus 5x minus 3, which is exactly what I want. So this is what I'm looking for right there. So, okay, so this can be written as the limit as x approaches 3 of x minus 3 times 2x plus 1 over x minus 3. These cancel. Now we have this is equal to the limit as x approaches 3 of 2x plus 1, or in other words, this is equal to 7. So this limit is equal to 7, but f of 3 is equal to 6. So again, the limit as x approaches 3 of f of x equals to 7 does not equal to f of 3, which is equal to 6. And that is why there's a discontinuity. I haven't been drawing the graphs for a lot of this stuff, but that's simply because that I don't have any intuition of how this stuff looks. I mean, you can kind of draw it based on what you know is going on in the area that we looked at. Or you can kind of draw it around 3 with like this discontinuity, but other than that, I'm not going to be able to actually draw it. So now let's look at problem 21. So it asks us to explain using theorem 4, 5, 7, and 9 why the function is continuous at every number in its domain, and state the domain, right? So first one, we have f of x equals x over x squared plus 5x plus 6. So let's first assume that x squared plus 5x plus 6 does not equal 0. Let's first assume that. Well, when we assume that, by theorem 4, we get that, so if we have a function, theorem 4, part 5 states that if you have two functions, f and g, that are continuous at some point a, then the following functions are also continuous at a, f over g, right? So our functions, f of x is going to be x, and g of x is going to be x squared plus 5x plus 6. This, of course, is assuming that g of a does not equal to 0. So over here, we're assuming that we're taking all a's such that x squared plus 5 squared plus 6 does not equal 0. And so then we have that f of x over g of x, or in other words, x over x squared plus 5x plus 6 is continuous by theorem 5. This is wherever we don't have a 0. So now let's look at the cases. So anytime the function x squared plus 5x plus 6 does not equal 0, this is continuous. That we understand, because that if the function does not equal 0, using Theorem 4, we can say that, listen, f of x is continuous, it's x, and x is continuous. And g of x, again, is a polytope, not that, it's a polynomial. Polytopes are like, I don't know, triangles and squares and stuff like that. So it's not a polytope, but it's a polynomial, and Theorem 5 says that any polynomial is continuous everywhere, that it's continuous on the interval negative infinity to infinity. So this is continuous and this is continuous individually, f of x and g of x. So then by Theorem 4 we can say that one divided by the other is continuous, again provided that g of x does not equal 0, because that's part of the condition. We need that g of a can't be 0 for the a. So we're choosing a's such that this is not equal to 0. So now let's imagine that it is equal to 0. Let us imagine that x squared plus 5x plus 6 does equal 0, or in other words, x plus 3 times x plus 2 equals 0, or in other words, x equals negative 3, or x equals negative 2. In both of these instances, x equals negative 3 and x equals negative 2, we have that this is equal to 0. And so we cannot make the claim that we made. But in both of these cases, let's look at this function. So in both of these cases, we have the limit as x goes, let's say, to negative 3 from the left of x over x squared plus 5x plus 6. Well, over here you have, this is basically 3 over 0. This is smaller, x squared is smaller than 5x, and the plus 6 does not really matter for the sign. So when we're approaching the left, we're going to go to negative infinity. So this is going to be like 3 over like an epsilon, meaning a really, really small number, 3 over, but a negative really small number, and this is going to be negative infinity when we're approaching from the left, because this is smaller than this. So so even though this is positive, this is negative, it's a negative number, and it's really close to 0, this entire number, but this negative number kind of wins. Oh, well, what am I saying? No. Okay, it's negative up here. There's a negative 3 because there's a negative 3 here. And frankly, I'm not really sure. I'm not really sure whether this is negative, is really small negative or really small positive. But regardless, coming from the left, it can be negative infinity or whatever, positive infinity, or it can, and the limit might even exist. I don't know. I'm not gonna like graph it or anything. But whatever it is, it's going to either negative infinity or positive infinity, and the same thing is true for the limit. As x goes to negative 3 from the right, this is going to negative infinity or positive infinity or something. Same thing is true for negative 2. Same exact argument. You're going to have a constant up here, which will be negative 2 over epsilon, where epsilon is very small. So again, you're going to have either a negative infinity or positive infinity. In all those cases, 3 will not be, negative 3 will not be in the domain, and negative 2 will not be in the domain, because you cannot have a number such that f of that number is equal to infinity. That's not defined. So in all those cases, the domain will not include negative 3 or negative 2, so we can say that on the domain, f of x is continuous, because the -3 and -2 are not going to even be in our domain. And our domain will look something like this: -infinity to -3, not including, open bracket, or also not including -infinity. -infinity, not including 3, right? So we're going to have this union, so adding -3 to -2, not including -3 or -2, and then union -2 to infinity. This is our domain, right? Or in other words, the domain -infinity to infinity without including the elements -3 and -2. So yeah. Next problem. Okay, so now I am going to do problem 22. So problem 22 says g of x equals equals 3x times 1 plus x to the third. So we know that the square root of x is only defined over the positive numbers, right? 0 to infinity. Why is that? Because that the square root of x takes a number and asks us what number, if I multiply that number, I am going to get, if I multiply that number by itself, I'm going to get x, right? So it's basically, it's finding a number, whatever, 0.5, I don't know, such that if you take 0.5 times 0.5, you get x, whatever, right? The number being given over there. That's what the function is basically asking. And you can never do that and get negative numbers, right? You can never take a number, no matter what number, negative or positive, and multiply it by itself and get a negative number. So that's why it's only defined over the interval 0 to infinity, because you cannot get negative numbers from this function. You can never ask what number, if I multiply it by itself, I'm going to get a negative number. That's impossible. But for for this function, there are numbers that if you multiply them by themselves 3 times, you get negative numbers. Like you take, I don't know, -1 times -1 times -1 gives you -1. So there are numbers that if you multiply them 3 times, if you multiply them by themselves, you'll get a negative number. So actually this function is defined everywhere, from -infinity to infinity. So this function is defined everywhere, and this function is defined everywhere. Polynomial 1 plus x to the third is defined everywhere. And we know from Theorem 7 that root functions, so here's a root function, or polynomials, so here's the polynomial 1 plus x to the third, are continuous in their domains. Well, the domains of both of these functions is -infinity to infinity, so as individuals, take f of x to equal 3 whatever, and take g of x, little g, this big G, to be 1 plus 3 to the third power. Well, as individual functions, f of x and g of x are defined everywhere. So now we can use Theorem 4 part 4 to say, well then, f of x times g of x, which is equal to this, 1 plus x to the third, which is equal to g of x, is also continuous everywhere, right? Because if f of x and g of x are continuous at a constant, then the other functions are also continuous at that are also continuous at the constant a. So these are continuous for any a and c, and these are continuous for any a and c, so these are continuous for any a and c. In other words, g of x is continuous everywhere for its entire domain, and its domain is negative infinity to infinity. So that's that problem. Well, I might actually have to make 2 videos for continuity too. We'll see. So let's look at problem 23, which says r of x is equal to x squared plus the square root of 2x minus 1. That's r of x. So x squared is continuous, is defined everywhere, and it's continuous. It's defined everywhere from negative infinity to infinity, and it's continuous everywhere. So the question is, where is this defined, and where is it continuous? Well, it's defined, we never want, so if you have like the square root of x, you don't want x to be less than 0. This is not allowed, right? Because then you're going to have a problem, which I just talked about. So now, when you have the square root of 2x plus 1, you don't want 2x plus 1 to be less than 0. Or in other words, you don't want 2x to be less than 1. Sorry, this is a negative. Okay, I'll redo it. So you don't want 2x minus 1 to be less than 0, or you don't want 2x to be less than 1, or you don't want x to be less than a half. So the domain is all x's such that x is greater than a half. So we go from a half, including a half actually, because that it can be equal to 0, right? The square root of 0 is just 0, so this is really equal. That's what we don't want, so this is not equal actually. So this is less. But now we're just taking its complement, meaning we're taking all x's that are bigger than a half. Well, that includes a half, bigger or equal to a half, that includes a half. So this is from a half to infinity. That's where our function square root of 2x minus 1 is defined. Okay. Then, so let's call f of x equals x squared, and g of x equals the square root of 2x minus 1. This is defined from negative infinity to infinity, and this is defined from negative infinity, from a half to infinity. There's like music going on outside, and I'm sorry about that. If you can hear it on the recording, I have no idea. So now, and it's not very good music. Any polynomial, right? So we know from Theorem. We know from Theorem 7 that polynomials are continuous everywhere they're defined. This is a polynomial, it's continuous everywhere it's defined from negative infinity to infinity, and that root functions are continuous everywhere they're defined. So this function is continuous everywhere it's defined. And then from Theorem 4, part 1, we know that f of x plus g of x is continuous everywhere that f and g are defined. And so we can conclude that r of x, which is equal to f of x plus g of x, which is equal to x squared plus the square root of 2x minus 1, is continuous and defined on the interval from a half to infinity. That's the solution to problem 23. Okay, let's now look at problem 24, which says h of x is equal to sine x over 1 plus x plus 1 plus 1. Okay, so let's first assume, like we did before, that x plus 1 does not equal 0, and we'll take f of x equals sine of x, and g of x equals x plus 1. Right, we're going to do that. So now so now f of x is defined everywhere because it's a trigonometric function. This is 7, and this function g of x is continuous because it's a polynomial. So now, again, because of theorem 4, part, I believe 5, we have that h of x, which is f of x over g of x, where g of x is not equal to 1, is 0, I mean, is continuous, so h of x is continuous. Now, when x plus 1 equals 0, or in other words, when x equals negative 1, we have sine of negative 1, which is not 0, it's some constant greater than 0, I'm not sure, divided by something approaching 0, getting closer and closer to 0, or whatever, epsilon limit as epsilon goes to 0, and this is plus and minus infinity, depending on whether you're approaching from the left or from the right. So because of this, it's not defined for x equals negative 1. So its domain is negative infinity to negative 1, together with negative 1 to infinity, not including negative 1s and infinity. So it is continuous everywhere it's defined. It's defined on this, and it's continuous in that interval too. Okay. This problem. Let's look at problem 25. H of x equals cosine of 1 minus x squared. So we can take if we look at theorem 9, we can take g of x to equal 1 minus x squared, and f of x to equal cosine of x, right? And then g of x is continuous everywhere, defined everywhere, because it's a polynomial, and cosine f of x is also continuous everywhere and defined everywhere, because that it's a trigonometric function. And so therefore we have f of g of x is equal to cosine 1 minus x squared is equal to h of x, right? Everywhere we see an x everywhere I see an x, when I put in g of x, I just put in this. So this just goes right into that x, and that's the same as h of x. So then by theorem 9, right, it says if g is continuous at a and f is continuous at g of a, then their composition is also continuous at a. And for us, they're continuous at all a's, right? G is continuous at all a's, f is continuous at all a's. So this, or this, or this, continuous at all a's, or continuous everywhere, and its domain is everywhere. So that was problem 25. Problem 26 is similar. Problem 26 says h of x equals tan 2x. Just take g of x equals 2x. F of x equals tan x. Tan x is continuous everywhere it's defined. It's not defined everywhere. goes to positive and negative infinity quite a lot. But everywhere it is defined, okay, that's not how it looks, but whatever, just graph it. Everywhere it is defined, it is continuous, and so we have that f of g of x is equal to tan. Also, g of x is continuous everywhere because it's a polynomial. Not a polynomial, yeah. Tan of 2x is equal to h of x. That's problem 26. If I was really quickly, I might finish on time. No, I'm not. I'm gonna probably make another video, or I'm just gonna go like 20 minutes. Oh, I know there's so many problems here. Yeah, I'm gonna stop in an hour when it reaches an hour and just make another video about continuity. I mean, it's important, and a lot of tests have a lot of questions about where functions are defined and where they're continuous, and so all of these problems are interesting and important problems, so there's no reason why not to do them. So now we have f of x is equal to the square root of x sine of x. So let's take little f of x is equal to the square root of x, and g of x is equal to sine of x. Also, breaking down functions into components like f of x and g of x is very important, because when you get to the product rule and the chain rule and the quotient rule and in derivatives, all of this is going to kind of rear its head, at least to some degree. So that's all important, I guess. So f of x is continuous where it's defined, which is the interval 0 to infinity. We spoke about this. And sine of x is continuous everywhere because it's and it's defined everywhere because it's a trigonometric function. That's why it's continuous. Everywhere it's defined, and it goes like that, whatever. If this is 0, so something like that. So it's defined everywhere. So because of that, again, using fourth theorem, you have f of x, g of x, which is equal to this, which is equal to f of x is defined. It's continuous everywhere it's defined, which is on the interval 0 to infinity. Okay, next problem. Okay, last one of these problems, problem 28. We have f of x is equal to sine, cosine, sine of x. So let's take sine of x. Let's take f of x equals sine of x. G of x is equal to cosine of x, and so g of f of x is equal to cosine of sine of x, and f of g of f of x is equal to sine of cosine of sine of x is equal to f of x. So we know that f of x is continuous because it's continuous everywhere it's defined everywhere, and g of x is continuous, and it's continuous everywhere it's defined, and it's defined everywhere. So because of that, by theorem 9, I believe, we know that g of f of x, which is this, is continuous, and it is continuous and it is defined everywhere. So we can say that, let's say this is h of x. H of x is equal to that. So this is going to be the same as f of h of x, but h of x is continuous and defined everywhere, and so again, and so is f of x. So again, by theorem 9, we have that this is continuous, or this, so f of x is continuous everywhere it's defined, and it's defined everywhere. Okay, so we just reached the hour. So what I'm going to do is I'm going to start another video for continuity, and I'm basically going to go through like problems from 29 until I don't know, like 64. That should be an hour, hopefully. I don't want to make another video. 2 videos on continuity I think is plenty, so I'll try to run through it. So that will be the 6th video, and then I guess the 7th video. I always make plans and they never work, but whatever. The 7th video will be about the definition for derivatives. I really want to get to the heart-ish of calculus, which is derivatives. So I kind of want to move quickly. So hopefully by by 3 videos after definitions for derivatives and all that, and playing around with that a little, we'll finally get to like section 3.3 and 3.4. Is there a 3.4? Yeah, and 3.5, which chain rule and all that, and we'll get to do some derivatives. Hope this was helpful.